So let's do another Lorentz force example. So what is the force on a charge Q traveling at along the positive x direction at 50 kilometers per second? And so here's my Q, and it's going this way at v equals 50 kilometers per second I hat in a magnetic field, which is which is 10 Tesla J hat, right? And so for a force, since it's a vector, we want F equals QV cross B, right? And that's 20 microcoulombs times 50 kilometers per second times 10 Tesla. Times I hat cross J hat. Right, I just pulled the magnitudes out since they don't matter. Well, they just factor out if you want. You could just as easily write it this way: 20 microcoulombs times 50 kilometers per second I hat cross 10 Tesla J hat, like that. And we can see if I put my arm along I hat, curl my fingers towards J hat, my thumb points up towards K hat, and so I hat cross J hat is K hat. And so we could say 20 microcoulombs times 50 kilometers per second times 10 Tesla K hat. And so 20 times 50 is 1,000, times 10 is 10,000, and so it's equal to 10,000 microcoulombs times kilometers per second times Tesla. And so micro times kilo is 10 to the minus 3 times 10,000 is just 10, and that's coulombs meters per second, right? And if you remember, Tesla was Newton over coulombs meters per second, and so that's 10 newtons. That's a pretty big force. If we wanted to go back, we could go all the way back to our definition of the cross product, and we could say, look, F equals QV cross B, and we could say that's equal to Q times I hat, J hat, K hat, right, across the top row. This is the determinant, that's the definition of a cross product, right? And so V hat would be 50 kilometers per second along I hat, 0 and 0. It's got nothing along the J hat, and it's got nothing along the K hat, right? Similarly, B is 0, 10 Tesla, 0. Right. And so when we take the cross product, it's equal to I hat times that minus that times that, so it's 0 minus 0, minus J hat, that times that minus that times that, so 0 minus 0, plus K hat, that times that minus that times that. 50 kilometers per second times 10 Tesla. It's exactly what we got here, right? And so this is, once again, it's 20 microcoulombs times 50 kilometers per second times 10 Tesla, which is 10 newtons. Generally, it's easier if the vectors are simple to get to just use the right-hand rule. If the vectors are a little more complicated, if the velocity is 10 meters per second I hat minus 2 meters per second j hat plus 7 meters per second k hat, and the magnetic field is also some combination, this is probably the easiest way to do that. It's also worth noting that you can use the right-hand rule. So if this is my coordinate system, this is my x, this is my y, and this is my z, where the x is coming out of the board. Again, you have to use your right hand to make a coordinate system. Oops, I'm a little off the screen there, aren't I? Let me see if I can tip that a little bit. That helps. My index finger is my x-axis, my middle finger is my y-axis, and my thumb is my z-axis, so I do it like that. Right. And so this is the I hat, this is the j hat, and this is the k hat. You can see just by using the right-hand rule that I hat cross j hat is equal to k hat. J hat cross k hat is equal to I hat, right? If I put my arm along j and curl my fingers towards k, my thumb comes out of the board, and so that's I hat. And then I hat cross k hat. So now I'd have to have my thumb coming out of the board and curl up towards k. I would get my j hat, I would get a minus j hat. And so you can generally just, if you just have a simple situation, you can just figure them out by hand or remember them or something. But you can always go back to the long definition if you need it. So a few things about magnetic fields. There are several ways to represent magnetic fields. So magnetic fields are continuous loops. I should say magnetic field lines are continuous loops. These are how we represent. So if this is my north pole and this is my south pole, my field lines, I would draw them like this, where the field points this way on the outside and that way on the inside, obviously. And so you'd have that, and then that would come around, and that, and then you'd have this guy somehow like that, like that, and like that, and so these guys would all be pointing this way, and so you can see your field is strongest where the lines are densest. So this would be like 1, 2, so if I ask the question, what's the direction of the magnetic field right here? It's just tangent to the line at that point, and so it would be like that way. What is it over here? Well, it's in this direction, right? It's tangent to the line at any point. Like right there, it's pointing that way, say, right? And so on. just like with electric fields. Many of these are very similar. Field strength is proportional to line density, so it's stronger there than it is out here. This is the Ghostbusters rule, just like for electric fields. Almost for the same reason. If you have lines crossing and you want to calculate a force, you don't know which line to use, and so it would be you could have the same field providing a force to a charged particle in different directions. I think that's about enough for those guys. And so, you know, you could, I could just draw an example or two just right on here, like, if I have a North Pole here and a South Pole here, you know, I'll get this sort of effect. Something like that, right? If I have two North Poles, field lines are kind of repelling each other, you might say. Right, the field lines are essentially spreading away from North Poles and looking for South Poles, and so those are two examples of those. So this is motion of a charged particle in a magnetic field. We're going to say we have some particle Q, and it's moving with velocity v, say in the plus x direction initially, right? And so v is equal to v I hat. The magnetic field is pointing out of the board. Those are the arrow tips, right? And so b vector is equal to b k hat. So my coordinate system is going to look like this. It's going to be my x-axis in this direction, and I want my z-axis to point up, and that puts my y-axis up the page. And so it's still a XYZ coordinate system like we've been using. It's just rotated maybe a little differently, or oriented a little differently. And so we want to know what happens to this particle, right? And so hopefully we can realize by now, right, that the force is equal to QV cross B, and that's equal to Q times V I hat cross B K hat. And we already know what that is. That's QVB times minus J hat. But we could have done that just by hand if we take our right hand and lay it along V to the extent that we can, curl our fingers up towards B, and then point this way for the direction. It would be in the minus J hat direction. And so the force is this way. Right? And so notice that the force is directed perpendicular to the velocity, right? Not only that, but so that's going to cause the direction of the velocity to change, but not its magnitude, right? Because it's perpendicular, it's not going to speed up or slow down the velocity, it's just going to turn it. And so an instant later it'll be going this way. It would have been going this way, right? It gets turned a little bit, and now it's going this way. But guess what? If you use the right-hand rule again, the force is still going to be perpendicular, because now my direction is, say, this way, and if I curl my fingers, I still have a direction that's perpendicular. And so the F keeps staying perpendicular to, this is V, this is V, the F is constantly perpendicular. Well, this is a picture of centripetal forces acting, right? if my force is constantly perpendicular to the velocity, that's circular motion. And so what we can say is that the sum of the forces equal to mass times the acceleration. That's equal to mv squared over r. And that means that qvb is equal to mv squared over r. Notice I've dropped the directions out of here, right? This force is directed towards the center of whatever circle. It's perpendicular to the velocity, which is towards the center of the circle. And this acceleration is directed the same way, towards the center of the circle. And so even though if I was to write this in an XYZ coordinate system, all these vectors would be changing. If I do it relative to the circle, this is what I get. I can just drop the directions and say towards the center. Right, and then, and so this is the equation. I can solve for r if I want to. I can say, look, the radius of the circle is equal to mv squared over qvb. And that's equal to mv over qb. So the radius gets bigger if my mass is larger or my velocity is larger. The radius gets smaller if my charge is bigger or my magnetic field is bigger. The magnetic field tends to tighten and the charge tends to tighten the circle up. They increase the force, right? But preferentially, the mass and the velocity want to keep the thing going in whatever direction it's going. The faster it's going and the more mass it has, the harder it is to turn. The greater its charge and the stronger the magnetic field, the easier it is to turn. And so this tells me the radius of my circle. And so there are a lot of things to learn from this, but this is how cyclotrons work in particle accelerators or something. They use enormous magnetic fields, for paths that are miles in diameter and enormous velocities, and they do this calculation to just figure out what velocity and energy they can get on a particle in a given size. In a given size path. So hold that, put a pin in that for a second. If V is parallel to B, if they're in the same direction, QV cross B is 0, because the magnitude, which is QVB sine theta, is 0 because theta equals 0. Right. You can just as easily just pick your cross product this way, right? If I take V cross B and I just pick them along one particular direction, I hat, J hat, K hat. If I say let me just put them along the I hat direction just for simplicity, right? 0, 0, B, 0, 0, right? Then this is equal to I hat times that minus that times that, so 0 minus 0, minus J hat, that times that minus that times that, which is 0 minus 0, plus K hat, that times that minus that times that, 0 minus 0 is 0. So so we can go back to if the velocity is parallel to the magnetic field, it has no effect on it. So now we can go back to looking at the problem we had a second ago, where I had a magnetic field look like this. And now let's say my charged particle has a velocity, has a component. So this is the y-x plane, and the z plane is coming out of the board. Let's say this is my v sub x, but I also have a v sub z, right? And so the x component of the velocity will cause my particle to circle. But the z component is unaffected. There's no effect due to the force, due to the velocity in the z direction from this magnetic field. And so the particle will spiral upwards. Its z component of velocity is unchanged, but its x velocity is causing it to spiral. And so it'll start out and it'll just do this, spiraling along with its z component. This is what happens when charged particles enter the Earth's magnetic field or any planet's magnetic field. The part of the velocity that's perpendicular to the magnetic field they're going into causes it to go in a circle. The part that's parallel is unaffected. And so if you have an Earth, right, here's my Earth, and these are my magnetic field lines, something like this, right? Then a charged particle will do this, something like that. And what that does is it causes the particle to take much longer to get through the atmosphere. And so it dissipates its energy before it, say, gets to the surface of the planet or does too much damage. It just spreads its energy out by vastly increasing the length of its path and dissipating its energy. These are the things that cause the northern lights or the auroras, the northern lights and the southern lights at both poles. I didn't do my south pole very well. Of course, I didn't label either pole, so you don't know which one I was doing. But anyway, magnetic field's stronger up here. You get more of an effect in here, and so we get ionization in the upper atmosphere in these regions, and we see the lights from these particles from the sun that are ionizing the atoms in the upper atmosphere. Eventually, those atoms sort of recombine. The energy gets dissipated with no significant harmful effects, and a lot of things happen. We get to hang on to our atmosphere. It doesn't just get chiseled, sandblasted away, and we don't get to be bombarded by these high energy particles. By the time they get down to the Earth, they've lost all their energy. By the time they get down to the surface. Planets that lose their magnetic field because their geology has died, because they've cooled off in their core, these high energy particles can just come all the way into their atmosphere. You know, on the scale of the Earth, the whole atmosphere of the Earth would probably be that black line. All right, 80% of the atmosphere is in the first 10 miles. The radius of the Earth is 4,000 miles, so a tiny fraction of its surface is above its surface is the atmosphere. And so all the relevant atmosphere is very close. The magnetic fields go way out, and so by the time anything gets in close, it's lost all its energy. If you don't have your magnetic field, then the particles can come in and chisel your atmosphere away, sandblast your atmosphere away. And that's sort of what's happened to Mars, that and other things. An alpha particle, which is just a helium-4 nucleus, is 2 protons and 2 neutrons. Its mass is consequently 6.64 times 10 to the minus 27 kilograms. Its charge is 3.2 times 10 to the minus 19th coulombs. This one travels in a circle of a radius 0.25 meters or 25 centimeters in a magnetic field of 1.5 Tesla, right? And so we can just have it going, say, this way. That's its velocity. And here's my radius. And then so on. That's my magnetic field, right? And then QVB has me always going in the center when I'm going this way. Force is that way, force is always towards the center. And so I get sum of the forces equals MA equals MV squared over R. And that's QVB is equal to MV squared over R. We're solving for V. And so we can cancel one of the V's. And then we get V is equal to QB R divided by the mass. And so we just have to multiply that out. It's 3.2 times 10 to the minus 19th times 1.5 times 0.25 divided by 6.64 times 10 to the minus 27. And I get V is equal to 1.81 times 10 to the 7th meters per second. So a significant fraction of the speed of light. Question B says what's its kinetic energy in joules and electron volts? And so its kinetic energy in joules is just 1/2 mv squared. And so that's 1/2 times 6.64 times 10 to the minus 27 kilograms times 1.81 times 10 to the 7th meters per second squared. One joule, 1 electron volt is equal to 1.6 times 10 to the minus 19th joules, and so I can say the kinetic energy is equal to 1.08 times 10 to the minus 12th joules times 1 eV over 1.6 times 10 to the minus 19th joules, which is 6.8 times 10 to the 6th electron volts, and so the kinetic energy is 6.8 million electron volts. We write it that way. So the energy is just all the potential energy converted into kinetic energy, and so it's equal to QV. But since we're doing it in electron volts, we get 6.8 times 10 to the minus times 10 to the 6th electron volts is equal to QV, but the Q is just 2e because it's just twice the charge. It's just 2 protons times the voltage, and so V, the e's cancel, and we get V is equal to 3.4 times 10 to the 6th volts. We could also, if we wanted to, wasn't in the question, but I could say right, we're going to ask what the period of the particle is. That's the time it takes to go around once, right? The velocity is equal to the distance over the time, right? And so that's equal to 2 pi r over the period, and so the period is equal to 2 pi r divided by the velocity. And so all those numbers are sort of given in the problem, and we can say 2 times pi times 0.25 divided by we calculated the velocity, didn't we? Hang on a second, I've just got to dig it back out. So it's 2 pi times 0.25 meters divided by 1.81 times 10 to the 7th meters per second, or the period is equal to 8.7 times 10 to the minus 8th seconds. So 87 billionths of a second. It's pretty fast.